Okay, so good morning, ladies and gentlemen. A very warm welcome to all of you to this school come workshop on data analysis in cosmology and astroparticle physics, organized by the Technology Innovation Hub of Indian Statistical Institute. As all of us know, cosmology there has been a paradigm shift in cosmology in the last 2 decades. It has transformed from primarily a theory-based subject to a data-driven subject. We have got plethora of data in our hand, and we need to keep ourselves ready to analyze that data and extract out meaningful information about our universe. So I think that this is a very timely program, in particular for the young people who are sitting over there, to get to know about the state-of-the-art technologies and techniques about cosmology, both from the theoretical side as well as from the data analysis side, from the experts, and to take part in the hands-on sessions so that you can equip yourselves to work in these fields. So this is primarily the basic motivation of this program, and this is going to be held in the next 2 weeks or so. So I would urge the young people to take maximum advantage of this kind of program, so to say. Okay, so I will basically make a couple of announcements before I hand it over to the speaker today. First of all, most of you have been sent an invitation in Slack. So please follow the Slack announcements over there and discussions over there. You have been sent an invitation to Sci server as well. So please accept that invitation. You'll be guided to a folder which is Workshop ISI, and some basic information regarding the data as well as the codes and etc. that will be shared over there, and you need to make use of that. Third one is regarding the Google Colab. You'll be given instructions on how to use that, but you must have Gmail ID, and most of you have shared that. Those of you who have not yet shared your user IDs for Sci Server and Google Colab, please do it as soon as possible, because otherwise you won't be able to take advantage of this program. Next one is there has been slight change in schedule because of some unforeseen circumstances that one of the speakers, Professor Surud More, he has got suddenly ill. So we had to reschedule the program slightly. So today, so there is a request, please keep yourself muted for all the time except when you are asking the question. Okay, so today both the talks will be given by Professor Anjan Ananda. Tomorrow there will be off day because we could not adjust that day. Day after tomorrow, first talk will be given by Professor Tirthankar Raichaudhuri, and then rest of the programs will follow as scheduled. So this is something you need to keep in mind, and you need to check the Slack and etc. Time and again, so that if there is any update, you get to know about that. Please join at least 10 minutes prior to the program in each session so that you can begin in time. And as I said already, please keep yourself muted throughout the program and your videos off so that you can save the bandwidth. Whenever you have some question, you can ask the speaker, depending on how the speaker wants to proceed. So if he wants to take the questions at the end of his talk, that is also fine. Or if you want to interact and discuss during the session, then only you need to unmute yourself and ask the question. So with all this brief introduction, let me begin by introducing our speaker today, Professor Anjan Ananda, who is a professor at Ahmedabad University right now, and he has been working for several years on dark energy, large scale structure, 21 centimeter cosmology, and lots of other aspects of cosmology as well. He is a member of Square Kilometer Array, 30-meter telescope, and some other international mega projects. And he'll be discussing, in these 2 lectures, he'll be discussing the basic cosmology aspect. After that, he'll be take off dark energy aspects later on towards the later part of this program. So over to you, Professor Sen, the stage is yours.
Yeah, thank you, Shubhrati, for the introduction. And hi, students. So in this these 2 lectures, we have this basic cosmology. So what we'll do actually is just to set a ground for the background cosmology, so that afterwards, it means there will be more advanced topics like CMB, 21 centimeter, large scale structure, dark energy concept. So these 2 lectures will be just focus on the basic background cosmology. In the second lecture, we'll try to introduce some hands-on session. There is one of another postdoc with me, Manavendra. So he will share you some details about that, how to proceed. So for those for the hands-on, so he will give you all the information regarding that. So what I will do there, I will not show you slides. So I thought that for this basic part, maybe it is better that I do things. Means like what you we should have done if there is no pandemic, like doing things on the board. So I use some sort of a Jamboard and I do these things so that you can see all the calculations. I thought that for basic part, it's necessary that you go through all the calculation or the basic concept rather than showing the slides. What we'll assume that I will not do any sort of complicated stuff for general relativity, but I will assume that all of us have some basic idea about general relativity, about the curvature of space-time and those things. There means we'll not do any calculation related, related to that, but we need those concepts time and again throughout these lectures. Right? So I hope you have that thing. As Supratim said, if you want, you can stop me and ask questions, or you can write things in the chat box so that I can at some time I can see at the chat box and I can discuss whatever queries you have. And obviously at the end of the class, you are free to ask any question or whatever the chat box is there that I missed that that we discuss. Okay. So what I will do, I will share my screen. Yeah, can you see my screen, everybody?
Yes, sir. You can see.
Okay. Yes.
Fine. Okay. So, so what we will do is basically that our basic motivation for these two lectures is that how GR describe the evolution of universe. So that is our goal in this lecture, right? And before starting that, let's just discuss some length scale that we'll use in our all the calculation or all the discussion. We'll time again say all the scales. So one typical scale that we use in cosmology is what is called the parsec. Or okay, so that we'll use that scale that we use, and what that is actually. What is this parsec is defined that let's say that you have, let's say, the sun at the center and earth is moving fine around the sun, and it takes an year to go around the sun, and there is a star over here, fine, and this is the distance between the earth and sun, and we know that this is the distance is around 1 astronomical unit, and 1 astronomical unit is roughly 1.5 into around 10 to the power 11 meter. Okay, so that is between the distance between the sun and the earth. And let's say there is a star over here, fine. And as you go around, the earth go around the sun in a year. Okay, so let's say that if you see the star at the background of the other star, fine, and there is a parallax that you measure. Okay, and this is roughly around 1 arc second. Okay, so 1 arc second, you know that it is basically 1 by 3000 degrees, 3600 degrees. Right? That is basically 1 arc second. So if this parallax that we have is around 1 arc second, then this distance we call basically 1 parsec. Right? So that is the way we define parsec, and that we use to measure distance object. Right? The typical thing that is interested for us is around 1 megaparsec. So that is we are mostly interested with. Okay, and this is roughly 3 into 10 to the power 24 centimeter, and this distance is typically the distance between two galaxies. Okay, so that is that we have roughly, right? And now the other sort of distance that you can say is that like the observable universe, or the size of the observable universe. This is roughly around 3000 megaparsec. Right? So that is roughly the size of the observable universe that we have. And whatever the galaxy surveys that we see, different large scale galaxy surveys. Okay, so different galaxy surveys that we have. Okay, so they typically, the size of this, the kind of the sky they can, means they cover, is like few large megaparsec, fine. Means around, let's say, typically around 800 megaparsec or like that. Means like 700, 800 megaparsec or something, or little bit more, little bit less, fine. So that is roughly the kind of thing that you can see, that typical distance between two galaxies are roughly 1 megaparsec. The size of the observable universe is that, so that I can get information, I can receive light in the age of the universe, that is roughly around 3000 megaparsec. And the kind of galaxy surveys that we have typically around present time, they usually have a sky coverage of around 800, 900 or 700 megaparsec, a few large megaparsec. Okay. So that is roughly sort of a kind of size that we can talk about. Okay. In terms of this megaparsec. Okay. So now, given that, the first thing that we see, that we see in the universe, we see is that the universe is homogeneous and isotropic on large scale. Now, I'll try to explain each and every words in this thing. Fine. Now, when I say homogeneous isotropy, just keep in mind that this is homogeneous and isotropic in the space. Fine. Because homogeneous in time means that everything is same in all time. That means the universe is static. There is no evolution in the universe. But we know that the universe is expanding, and all this cosmology is dealing with that the universe is expanding. So we don't have homogeneity time. So we have homogeneity in space. Also, the time we cannot, it means we cannot rotate time. So there's nothing called what is called the isotropy in time. So what you call about homogeneity and isotropy, it is basically the fact that the space part of the universe is homogeneous and isotropic. And what does it mean when I say it is homogeneous? That means there is a kind of a translational symmetry. I go from one location to another location, and in that sense, the universe remains the same in different space locations. Fine. The only thing it goes is that time things change. Fine. And when I say an isotropy, that means there is a kind of a independence of the direction. So whatever direction I look at, the universe looks roughly the same. Fine. So that's what it means by homogeneity and isotropy. Okay. Now, when I call that, okay, homogeneity and isotropy on large scale, what do we mean by that? Right? So the first thing that you can see, okay, first let's say that whether this homogeneous and isotropy, they imply one, means if I have homogeneity, whether it is isotropy then also, or whether we have isotropy, then it is also homogeneous. So whether one implies the other, fine. But surely I can write a metric. I can write a distance between two space-time, a space metric, fine. Something like, let's say, s square t dx square plus b square t dy square plus c square t dz square, fine. Now, as you can see, that there is no space dependence in A, B, and C. So obviously, this matrix looks homogeneous. But this metric is not isotropic because the x direction stretched by a factor 80, the y direction stretched like a factor with a factor bt, and the z direction stretched by a factor ct. Fine. So all these directions stretch in different fashion. Fine. So this metric is homogeneous. I can call this metric homogeneous because there is no space dependence. But this metric is not isotropic. On the other hand, I can take a spherically symmetric space-time, or spherically symmetric space, rather spherically symmetric space, fine, which is isotropy, because spherical symmetry ensures that things are isotropy, fine. So I can take a spherically symmetric space, fine, which ensures that things is isotropic, because spherical symmetry means that there is no direction dependent, all the directions are the same. But we know that means if you have a spherical symmetric space, direction independent is there, but it may not, it may change at different space locations. So this may not be homogeneous. So these are okay. So that is possible, fine. So always that universe is there is a homogeneity we ensure, that doesn't mean the isotropy is automatically ensured. Similarly, if isotropy is ensured, that doesn't mean the homogeneity is automatically ensured. But what one can actually show, I will not go through all those geometry and all those things, that if you have at least 2 points, any 2 points in the means if there is spherical symmetry between any 2 points, fine. Then one can show that the homogeneity is ensured. Or in other words, actually, if all the space the location, there is the isotropy around all the space location in the universe, then it will ensure that the universe is homogeneous. Right? So in that sense, if there is a isotropy around all space location in the universe, then the homogeneity is ensured. But other than that, the isotropy doesn't ensure automatically. It can be isotropy and homogeneous, but isotropy doesn't ensure automatically that things have to be homogeneous. Now, so okay, so that means that what is homogeneity and isotropy, fine. But at the same time, if you take a three-dimensional universe, fine. If you take a three-dimensional universe in space, fine, and you assume the homogeneity and isotropy, then what one can show that this is the maximal symmetry that you can have in a 3D space, right? That is, so we have 3 sort of a conserved quantity coming from the homogeneity, 3 directions, and 3 conserved quantity coming from the 3 direction isotropy. So total altogether 6 conserved quantity, or in generality we call it 6 Killing vectors. So in 3D space, that is the maximum kind of number of Killing vectors that you can have. And in 3D space, homogeneity and isotropy ensure that the space-time is maximally symmetric. And if you have, so we call it a maximally symmetric space. That is the maximum or most number of Killing vectors that you can have. Symmetric space-time. Okay, so that is the most number of Killing vectors that you can have. Now, if in general relativity, one can actually show that if you have a maximally symmetric space-time, then the curvature is a constant. The space curvature, or if you have a maximally symmetric space-time in space-time, then the space-time curvature is constant. Here we have a 3D space, so it is a maximally symmetric, it's homogeneity and isotropy. So the curvature of this 3D space, you can, if I write it like 3R, the curvature, Riemann curvature for this 3D space, then this is a constant. And that also we can expect from homogeneity, fine, and isotropy, because universe is homogeneous at all points, fine. So that means each point has the same, all properties are the same, so as the curvature. So that means if you calculate the space curvature of this space, then it should be constant at all space. Right? So that is, and this, as I said, so this one expects for homogeneity. Okay, so this space that we talk about, for that we say that the universe has this homogeneity and isotropy, and 3D space is homogeneous and isotropic, and this space has a constant curvature, and that we'll see that how one can use this constant curvature. Okay. Right. Now the question is that what we talk about this homogeneity and isotropy, okay, from our observational perspective, because we know surely that as we look at the there are planets, there are stars, there are galaxies, there are cluster of galaxies. So obviously the universe is not homogeneous and isotropic, right? In that sense, right? Because there are some stars, there are some galaxies, cluster of galaxies in between, there are empty space. So So obviously, why we call it a homogeneous and isotropic. Fine. So what we, as I told you, that what you say is that the universe is sufficiently at sufficiently large distances. It looks like homogeneity and isotropic. Now, what I mean by that. So what I mean is that if I take a sufficiently large size box, and then take this box at different space location in the universe, and then we'll see that statistically different properties of inside the box is density, mass, or whatever, right? We can, whatever physical property that can associate with this box, statistically they remain the same. Fine. There can be fluctuation, fine, random fluctuation, but statistically, all this property of the box, this large box, if I take it at different space location, they remain roughly the same. Now I need to make it more precise. Fine. So how I can make it more precise? So let's say that I take a sphere. Let's say that I take a sphere of radius r, fine, and I put it at a space location x. X means x, y, z. So altogether I call it as x, fine. A space location, let's say x, fine. I put that sphere, fine. I can calculate its mass. If it is density, at that point I know I can calculate its mass, fine. So for the mass of that sphere of radius r with a space location, fine, x, fine, I can calculate it, fine. Then I take this sphere, okay, the same sphere with radius r, and I take this sphere at different space location. That means I am changing over the x, fine. If I do that, then what I'll see that there will be some random fluctuation of this mass, fine, depending upon different property at different space location. But now, if I calculate what is called the deviation from the mean, okay, I take the square of it, and I divide by this mean. Okay, so that means I am averaging over all these space location, fine. So if I do that, so I take it at different space location. All these space location has a lot of random points, fine, and I average it over that thing. I get a m bar, and I also calculate what is the fluctuation from this m bar. Okay, so that is delta m. If I do it, what you will find actually, so because now these things I have averaged over x, so there is no x dependent, so it only depends upon r. So this will be some proportional to function of r, okay. And what you can see that this actually sort of a kind of vary, because this is a dimensionless quantity, so some kind of a dimension full number, some length divided by the r, okay, to the power n. Okay, it doesn't matter that what is the n value, roughly n is 2. But let's say, so what you find that this actually varies like, so it actually varies like r to the power minus n. So if I take the size of the box different, or size of the sphere, the radius of the sphere different, this quantity actually goes like 1 by r, something like that. Okay. So now if I take r sufficiently large, okay, then I can say that this delta m will be very smaller than the m. And what this sufficient large r is, roughly this r, this r value is roughly around 200 megapascal. Okay, so you can, so that's actually sort of a kind of a more precise statement, that if I take this size of a universe which is around 200 megapascal, and I take this and I take that box, okay, and take a different location, statistically the properties of this box inside the box, whatever you have, they will be roughly the same. The fluctuation will be much smaller than the average that I can. So that what we mean, what I mean by form is that the universe is homogeneous and isotropic. I think, is there any question regarding that? Okay, it's not the three factor. Okay, so this is what I said where I wrote. Okay, this is not three factor. This is, okay, I should be, means like this is r, and I just put at the superscript that 3, fine. So this R3 means there is a Riemann curvature for the 3-dimensional space. Okay, so it's not 3 into R. Okay, my writing is not that good. So, or I can write it R3 actually. So this I just write 3 because in general when I write capital R, this says that the Riemann curvature of the fourth-dimensional space time. So here I just put a 3 over here, like to show that this is the Riemann curvature of the 3D space. Fine, it is not 3 into R. So that I should have been careful, but okay, it's like that. Okay, fine. Okay, so now let's say that what I need to do. So I have this homogeneous and isotropic space, right? I have to build a metric for that. Okay, and then I have to solve the Einstein's equation. Okay, giving some sort of a distribution of matter in the universe. Okay. So what I should do? So before doing that, so what we need to do? So we need to solve this Einstein's equation, right? So we need to solve this Einstein's equation, which is G nu, which is first term in the function of this space-time metric, which is the function of the space-time metric, small g nu, and that I need to solve for this this equation. Right? Okay, so given that I assume the homogeneity and isotropy of the space, I have to get some kind of metric from this symmetry. I'll do that very soon. And then I calculate the Einstein's equation in the Einstein metric or Einstein tensor, which are function of this metric, its derivative and its second derivative. And I equate it some matter distribution in the universe, and then I solve this equation. Fine. That is our goal. Fine. But now, as you can see that that this part, this matter distribution that I have over here, fine. We know that already we discussed that this distribution has like stars, planets, galaxies, super cluster galaxies, super cluster. So in general, this T mu mu that we have is not very homogeneous and isotropic, right? This is not. Okay. So what in principle people should do, what is the best way one should do? That one take not this homogeneity and isotropy, but taking all this sort of that we have, this inhomogeneity in the universe, take care of that, solve this thing, fine. You get a G nu mu, and then make this G nu mu average over a large box of 200 megaparsec. And that's the way you get a behavior of the metric or behavior or a background cosmology, a metric from the universe, which is valid at the large scale. Okay? So first we solve this equation, taking into account all the inhomogeneity we have in the universe, solve this G nu mu, fine, and then average it over a box size of 200 megaparsec, because we just argued that around 200 megaparsec is roughly the fluctuation is much smaller than the mean, right? So that we should have done, right? And as you can see, that would have been very difficult, because next we have means like once we have all these inhomogeneity, all these things, it's not very easy, right? Rather, what we do is that we actually take the average of this equation. We say that this is, I just take the average of this equation from the very beginning and solve this average. So what we are doing, so what one should have done, that solve this Einstein's equation, fine, for this G nu mu, okay, and then take the average, which we should have done. Rather, what we are doing, we are from the very beginning, we are writing the Einstein metric in terms of this average G nu mu, okay, and then we solve this equation, fine. So these are two completely different. You know that these two cannot be equal, right? Because the Einstein equations are highly nonlinear equations, right? So if you have a very nonlinear equation, then first take the solution of G nu mu and take the average is not equal to first take the average of small G nu mu and then write down the Einstein metric, right? These two cannot be same, as because the G nu mu part is highly nonlinear. Okay, if this capital G nu mu is like box of G, small G nu mu, then we could have done it, right? Because it's a linear operator, right? But as because it is not so, we have G nu mu, we have G nu mu square, its derivative is derivative square, all those terms are there. So these two things are not at all equal. But I mean, that is what we actually do with this thing. This is our approach, and this approach works, right? We exactly don't know why this works, but this approach is much simpler, obviously, than this, and this approach works, right? But then you can see that since people are coming like with the concept that okay, we have this accelerating late time acceleration or dark energy. Actually, this is an effect because we are not doing this kind of thing. We are doing this thing, which is actually not true. We should have done this thing, and if we could have done this thing, then maybe this dark energy effect or whatever we see is not a real effect. This is an effect because we are, instead of doing this, we are doing this, right? So those sort of things, we will see that there are papers and there are investigations on last thing, right? But on a whole, means what we usually do in cosmology, and this actually works perfectly with all the observation we can actually explain, we do actually this thing. Okay, so we actually take, okay, we assume that, okay, we first average my metric over this large box, and then we solve, we write down the Einstein metric and we solve, and later on to do the inhomogeneity, we just take perturbability, we calculate perturbability from this average G, how perturbability, linear perturbation, non-linear perturbation, we can add all those inhomogeneity and we solve those perturbation equation, and on those perturbation equation and try to calculate all those inhomogeneity in G and then that actually pretty much sort of explain whatever our current observation. So that you will do in your the previous next classes, fine. But just keep in mind that these two things are not the same, and they should not be the same. But we actually, our approach is basically this one. Okay, fine. Okay. So now as we know that universe is homogeneous and isotropic, so what kind of the most general space-time we can write, fine. So let's write down these means. Okay, so remember that I will mostly work in the unit when I will put C equal to 1, fine. So that is the thing that I will not, so for me, I will put my C equal to 1, fine. Okay, so the most general metric that I can write is maybe there is a G00 time with dt square. There can be some G0 alpha term into dt dx alpha. Let me write all the term first and then I will explain. And so this is a mixed term, and then there may be a term, there will be a term which is for only for the space part, which I write like this one, fine. And remember that the universe is homogeneous, so all these terms actually are only function of the time, because there is no inhomogeneity. Things are all same at all space locations, fine. So that's why all these terms should be only function of time. Now just come to this term. So G0 alpha is some sort of a vector, because these are this alpha thing, and alpha can go on from 0, 1, 2, 3. So this is the kind of a vector that I have, fine. Or this is T, so this is alpha is just 1, 2, 3. Okay, so this is can be 0, 1, 0, 2, 0, 3 that we can have, fine. So this is a kind of a vector, and we know that if I have this kind of a vector term, so it should give you a preferred direction. In general, actually, this term can actually related to a rotation in the space-time, and if you have a rotation in the space-time, there is a preferred axis about which there is a rotation happening, right? And we know that the universe is isotropic. There is no preferred axis, or there is no preferred direction or vector in the universe, right? Because of this isotropy. So this term actually goes to 0. Okay. Now come to here. This is a time-dependent term, fine. But what one can see that I can always sort of redefine my time to make it just dt squared. But what actually does it mean? It actually means is basically the fact that let's say that I have observer, okay, which are actually, so they are that are defined by this. So they are sitting quietly at space location, fine. So they are just static at the space location, x alpha equal to constant. And I define that whatever the time they measure should be the proper time. Okay, now you remember, you know that from your general relativity, this ds square or special relativity, this ds square is actually represent the proper time, right? So I am saying that my proper time is basically the time that is for the observer, which are actually x alpha equal to constant. Now, if I have x alpha equal to constant, so this term actually drops, fine. And then you come over here, then this, if this ds square has to be the proper time, then my g means that time should be the proper time, then my g00 should be actually 1, fine. So what I can put that this G00 to 1 for those observers, fine, for these observers, fine, which are actually constant, mean they are at x alpha equal to constant, they are located, right? Sometimes we call these observer called a co-moving observer, right? So we can call this observer co-moving observer. So in a sense, as the universe expands, they are actually going with the expansion of the universe. So in that sense, they are actually static, right? They don't see the expansion. Right? So for those co-moving observer, so I can put it 1. So finally, I can get a metric. And as I said, that this actually term drops because this can give you a preferred vector. And as because we don't have any, we have isotropy, so there cannot be any preferred vector. So this term drops. So the metric that finally I have is basically dt square minus gamma alpha beta dx alpha dx beta. Okay, so that is the metric I get. This part is basically the space metric. Okay, so this is a 3D metric that we have, and this metric actually have homogeneity and isotropy. Fine. So let's talk about this metric. Fine. So we have this space metric that we have, the 3D space metric that I have over here. Okay, so this metric, I call this is dl square. So this is this part. Okay. Now this metric overall it will have a time dependent factor, because that actually says that how the universe is expanding. But except that overall time dependent factor, this is a sort of a metric that gives you that what is the distance between two observer or two points in this 3D space. Fine. So this metric, and I know that this metric is homogeneous and isotropy. So in a so isotropy means that the metric cannot have any direction dependence. Right? So it's a spherical symmetry, right? In essence, right? So it can only depend upon r, but it cannot depend upon theta. Right? So I can write this thing. So remember that there is always an overall time factor that we call, sometimes we introduce that time factor. But other than that, just the fact that other than that overall time factor, this metric can be written. Okay, because of it's spherical symmetry. Fine, this can be written as some fr dr square plus r square d theta square plus r square sine square theta. This is overall a spherical symmetry metric that we have, right? Giving the isotropy. Fine. Now, as I said, so what is the FR? But I at the very beginning said that this is a maximally symmetric spacetime, and the maximally symmetric spacetime should have this 3 curvature should be constant. Okay, so I can calculate the Riemann curvature of this thing, this part. Okay, I can make it a constant, and then from there I can actually calculate this FR. Okay, so if I do that, this actually gives me this FR to be 1 minus some constant. This constant is related to this constant that I have, the 3 space curvature constant into r square. Okay, so this k is actually related to this constant. Right? But the idea is that I have this metric, which is a isotropic metric. I know that this is maximally symmetric space. Fine. That means it's Riemann curvature. This is the 3 space. Fine. So the 3 Riemann curvature has to be constant. So I calculate the 3 Riemann curvature from this. That will be a function of f1 and its derivative or whatever. Right. And then I make it a constant, and from there I calculate the FR, and the FR comes out to be this. Okay. So what then this metric, what I have over here, this metric now I have is dr square 1 minus kr square plus this r square, whatever, d theta square plus sine square theta. Okay. Now you can see that what this k, this r has a dimension length square. So this k, it is related to this curvature. So these are the dimension of 1 by L square. This is related to the 3 curvature. So it has a dimension of 1 by L square. So that's why it's a dimensionless. So this k is a dimensionful quantity with a dimension 1 by length square. So from there I can take it, let's say capital K. So from there I can always define a small k, which is this capital K divided by the magnitude of the capital K. Okay. So then this is a small k. So this small k then is basically a dimensionless quantity. Okay. Now I have so now if I write down this k, capital K is this small k into the magnitude of this. So if I put out over here, okay, then as you can see that I have to redefine my r. Okay, so I can redefine my r over here. I can redefine my r over here. So the overall factor will come out over here, and that overall factor I can always absorb. As I said, there is a arbitrary time dependence outside this. So this is the space part, but there is a time dependent factor a square t is there. So I can absorb this square with that whatever overall factor over here in that a. So that is not a problem. Fine. So then this k is basically a dimensionless quantity, and this is this k and divided by the k magnitude. So this can only take values 0, +1 or -1. If it is 0, then this is 0. This is k is 0, or depending upon whether it's a positive curvature or a negative curvature, this can have a value +1 or -1. Right? So now finally I can write this metric. The full metric now I can write is like the full metric. Now I can write is ds square. So the first term is dt square. Then there is the overall scale factor or overall time dependence is there. This gives the how the universe is expanding. And then here I have dr square 1 minus this kr square plus r square, this d omega square. Okay, so this d omega square is basically this part that I am writing, d theta square plus sin square. So that is my overall metric, and this metric and this small k can take value 0, +1 or -1. Right? And this metric is called effort W metric, Friedman-Robertson Walker metric. Okay, so this is the metric that we get, assuming that the universe is homogeneous and isotropic on large scale, and we define what is sort of a large scale in the size of around 200 megaparsec or so. I mean, this value is not, I'm saying very roughly, exactly what value we exactly don't know, but okay, around that value, this metric is valid. Okay, so this metric is valid over that value and means over that distance, and on small scale we need to incorporate the inhomogeneity and isotropy and all those things. So that is our metric that we have. Now, what is this metric? So now, as you can see, if k is 0, so if k is 0, this part is dr square plus r square d omega square. And we know that this is nothing but, we all know, fine. This is in the Cartesian coordinate, this is this, fine. So this is a flat Euclidean space, fine. Because I can do this transformation, fine. Like x is equal to r sine theta cos phi, then y is equal to r sine theta sin phi, z is equal to r cos theta, and then from here, or here r is 1, let's say r is 1, then I can get this part is basically this part, and this is just a flat Euclidean space. So this is flat. Okay, so for k equal to 0, this curvature is 0, so we just get a flat space. The 3D space is flat, fine. What happens when k equal to +1 or k equal to -1? Okay? So let's say that I take k equal to +1. Let's say I take k equal to +1. Then what happens? Then I have a term over here which is dr square into 1 minus kr square. So that is dr square 1 minus r square. Let's say I call this is as so if I have d chi square, let's say I just do a coordinate transformation. So my d chi is basically dr by square root of 1 minus r square. And from here I know that my chi is basically sine inverse r, or my r is sine chi. Right? Now, then what is my metric? So if I put it back over here, so this is my d chi square, and this part is my sine square chi. Fine. So what I have over here, that part, that dl square part, okay, this part is now d chi square plus sine square chi, and then inside that I have this d theta square plus sine square theta. Okay, now what kind of metric is, okay, what kind of metric this represents, right? So if you take a flat space, let's say I take a 3-dimensional flat space. Let's say I take a 4-dimensional space, flat space. Okay, then what is the metric of the 4-dimensional flat space? This is basically dx square 4-dimensional. So dx square, dy square, dz square plus dw square. So this is a 4-dimensional flat Euclidean space. And let's say I put a 3-sphere in so the constant on the 3 sphere will be what? X square plus y square plus z square plus w square equal to 1. Fine. So obviously this is a constant. This is the metric. I can actually replace. Let's say I can replace w in terms of x, y, z over here. I get a metric, and then what I do a coordinate transformation similar to the coordinate transformation I do from r theta phi to x, y, z. But here I have 4 coordinates. So I do a coordinate transformation omega, let's say, or with w or omega, whatever, let's say cos chi, and then my x is equal to sine chi. The rest remains the same, sine theta cos phi, y is equal to sine chi, sine theta sine phi, and z equal to sine chi into cos theta. Okay, and if you do this transforming, so first you take a 4D flat space, then you put a 3 sphere over there. So this is the constant on the 3 sphere. So the metric on the 3 sphere will be now you have to replace, let's say, this w in terms of x, y, z. You just put over here, and then do a coordinate transformation like this way. You get this exactly this metric. So just try to do it in your home. It may take half an hour, but you get this metric. So this metric is nothing but a 3 sphere. Okay, so this metric actually represents a 3 sphere, a closed geometry. And the important part over here, there as you can see, this r is sine chi. So this r, that coordinate that we have, is not in a sense kind of a distance coordinate, it's a periodic coordinate, the kind of an angular coordinate that we have. In general, when I write this, let's say in the flat space, when I have this r, the r goes from plus infinity to minus. This does go up to infinity. But here, when I have this kind of a metric, this r sort of a period, kind of an angular. Okay, so this space is actually represents points on a 3 sphere, right? Points on a 3 sphere. Similarly, if I have k equal to minus 1, I'll not do the thing, but let's say I have k equal to minus 1, then this dr square, this will be plus. Okay, so the d chi is dr square root of 1 plus r square. And if we integrate this instead of sine inverse, this will become sine hyperbolic r. Okay, and then r is sine hyperbolic chi. Then this metric will be d chi square plus sine hyperbolic square chi, this metric. Okay, and what does it represent? So again, you take a flat space, but try to put a hyperbola in it. So instead of x square plus y square plus z square plus w square equal to 1, put x square plus y square plus z square minus w square equal to 1. Okay, you put back over here, write the metric in terms of x, y, z, those things, fine. And then you do a coordinate transformation where instead of cos this chi term that I have over here, which is cos chi, sine chi, you just have cos hyperbolic chi, sine hyperbolic chi, sine hyperbolic chi. Rest remains exactly the same. Then you get a metric over here where this is instead of sine square chi, you have a sine hyperbolic square. So this metric for k equal to minus 1 represents basically a, so I can write that thing. So for k equal to minus 1, this dl square is basically d chi square plus sine hyperbolic square chi into that d theta square plus sine square theta d phi square. And this is kind of a hyperbolic geometry. And it's open geometry, right? So these 3 geometry that I have, k equal to 0, k equal to plus 1, k equal to minus 1. 0 is a flat space, okay, Euclidean flat space. The k equal to plus 1 is a 3D sphere, and k equal to minus 1 is a 3D hyperbola. Okay, so and we call it a closed because 3D space is a closed, so we call it a closed geometry, and hyperbola is open geometry. Right? So these are the space time that we have, fine. And what we have from here, Now, so that means this metric that I have, and what it now represents. So this actually now, so this is the full metric we have. This is the distance between two space point in this universe, fine. Depending upon what kind of A you have, and that is actually that distance is actually stretched by this scale factor 80, right? So what we have, if I can have a picture, let's say a 2D picture of that. I cannot draw 3D. So let's say I draw a 2D picture of that. So let's say I have a kind of a grid. Okay, let's say I have a kind of a grid like that at some time t equal to t1. Okay, and let's say each grid there is some galaxy sitting over here. What will happen? What is happening? So this distance, okay, between these 2 points or any 2 points, this distance is actually given by between this given by this thing, fine. This distance is given by this thing. But now because of this A factor is happening, because of this A factor is there, so what is happening that if I go to some time which is t greater than t1, so t equal to t2, which is greater than t1, then this box size is actually sort of increase, right? So again, the galaxies are actually sitting at the same space-time location, the same location they are sitting, fine. But only thing is that initially their distance is this, now their distance is this, and this increase is basically is due to that scale factor that I have, the A as a function of T. Okay, so that's the way the universe is expanding, fine. Now, one thing also I need to tell you, I'm not doing the calculation, but I just need to tell you. So let's say that initially I have this metric, fine. So I have this metric. So here this is there, and instead of later on I put this k as k by the magnitude of k. But let's say there is a k over here, which has a dimension of 1 by length square, and in with that there is a square t is there, fine. With that there is a square t, fine. What you can actually do is a very one-line calculation. It may take 1 minute. Okay, that if I scale this A by some like this way, okay, some lambda A. At the same time, I can scale by R by some R by lambda. And this curvature, it's that actual, the initial curvature. It's not the magnitude that I calculated, K by that K. But if I have this K, this also I scale like K by lambda. Also scaling by k by lambda, fine. Then you can show that the metric remains the same, fine. Or I think this is 1 by lambda, no, k lambda. Okay. So the metric remains the same. Okay. So I have this scaling is I have this is this in my hand. I can always change this. So I can take this thing. I can take this. That freedom that I have, that I can scale this A, and I can put the present day scale factor. So from now on, anything which is subscript 0, I call this is at the present time, T at the present, okay. I can put this A naught equal to 1, okay. So I can always set that, okay. Otherwise, in all this calculation, I have to always have a term like A naught by A or A by A naught, something like that. To make life simple, I can set the present day scale factor at 1, a value 1. That is the normalization kind of thing. Okay. Once I said that, I know that the universe is expanding. So at the earlier time, the A is smaller than 1. And when earlier time is earlier than today, and then any time later than today, A will be greater than 1. Right? So that is just a normalization I can do. I can just set the scale factor at present to 1. Fine. So that we'll do from now on. Right? So that we put that thing. Okay, there is some question. What is the advantage to define small k in the metric? The advantage is nothing. The advantage is that we just take a something that k, which is a dimensionless constant, fine, and I just put it and normalize. By doing so, I can keep it 0, +1, and -1. Right? That's the only thing advantage, right? So we don't need to actually think about what this value of curve, because that is the space-time curvature of the 3D space, fine. Sorry, space curvature or remain curvature of the 3D space. It has some value. Okay, but this value remains constant at different location. But then I have to always keep this value, and I have to in all my calculation, I have to take this value in that. Right? That maybe is bit inconvenient. You can do that. You can do that. There's no problem with that. Everything goes as it is, fine. But the thing is that just keeping a dimension full constant and keep taking into account every calculation may not be convenient. So that's why we just normalize in such a way that these whatever this means the curvature that I have, the space curvature, I just have some kind of a normalization thing that I do, and just I put it to +1 or -1. Then I don't need to worry about that, because whenever this value comes, I know that either it can take 0, it can take 1, or it can take -1. So that's the only 3 values it can take. Okay, I don't need to consider whether it is taking some dimension full number. Okay, so that makes things much more convenient. Right? It's just that. Yeah, that I said. That I said that I have to put it k. So this is r by lambda, fine. So you just say check it. Just check it. So this is k. Yeah. Thank you. Thank you. Thank you. So this is lambda square. Just a moment. What happens? Something got frozen. Can you listen to me?
Yeah, but the voice is a bit.
Yeah, I think there is some internet issue because things are now frozen actually. Just give me a time. Can I just Shupatim? I'm just logging it and logging out again. I think there's some internet issue. Things are sort of frozen. Just let me log out and log in again. Fine. Just Shupati.
Yes, sir. Yes, I'm here.
So,
Huh?
so you can just stop sharing and then start it again. That
Yeah,
will help you.
that's I'm trying, but
Yeah, now it's okay.
now it's open. I again start. Okay. Share thing. No, it's actually this thing actually is not coming up. So this is the problem of all this online thing. It's some sort of a. I just leave and I again log in. Fine. Maybe that may solve this problem. Just I am leaving and I'm again coming. Okay. Just give me 1 minute. Okay. Hello. Can you listen to me?
Yes, sir.
Yes, sir.
Okay. Let me start. Yeah, can you see? Means I'm just doing it now here. Fine, just maybe there is some issue with the thing. So I just do it here. Okay, so okay. So where are we? We are okay. Okay, so let me do it here. Fine. So what we have over here is that we have this ds square. Can you see this thing, everybody?
Yes, sir.
Okay, fine. Let it do it here. So I have this dt square minus whatever s square t, and then I have this dr square minus 1 minus kr square plus r square d omega square. So that is the metric that we have, right? Now, as I said, that this is my sort of distance between, means if I don't have this AT, so in the co-moving frame, so this is my distance between two space points, fine, this distance, fine. So the actual physical distance is basically is A into this distance, fine. So my R physical, I can define my R physical is basically the scale factor into this. This, let's say I called my X physical. And as I said that I have a co-moving observer. So this observer are all X alpha equal to constant, right? So my observer that we have are all X alpha equal to constant, okay? So this is actually not changing with time because these are my co-moving observers, right? All these things that the expansion that is doing and the physical distance between the galaxies are changing, they are because of the fact this A, because the A is actually is a function of time, right? Now, if I now calculate the velocity, the physical velocity that I have, that if I calculate the velocity R physical, okay, dt, okay, so this will be A dot into x, because these x's are not changing, they are just constant, fine. And now let's say I just replace this x by this r physical by a. So what I have is A dot by A into r physical. Okay. So my v physical, the velocity that I have as the galaxies are going, these two galaxies, they are going away from each other. The velocity with which they are going away from each other. Okay. So that velocity is basically A dot by A into the r physical. So that velocity is actually proportional to this their distances. Fine. Now this quantity that I have, A dot by A, okay, this quantity is called h, is a function of time, and we call this quantity a Hubble parameter. Okay. So what I have is my physical velocity that I have. Okay, the physical. Okay, this is your Hubble parameter. Okay, into the r physical. Okay. Now this is in a sense is the Hubble law that the velocity that with which the galaxies are going away from each other is basically proportional to the distance between them. Right. Now this Hubble parameter, as I said, this Hubble parameter, this in general is a function of time. Okay, is a function of time because the A is a function of time. But what we actually define and most relevant quantity is basically the Hubble parameter at the present day. Okay, as I said, anything subscript 0 shows that this is the value at the present. Fine. So the Hubble parameter at the present is roughly the value so as you can see that this is A dot by A, so it should have a dimension 1 by time. But rather than that, we actually we use the Hubble parameter as the basically how it defines is the velocity per distance, right? So that's why we write it as 70 kilometers per second per megaparsec. Okay, but it says that if two galaxies they are separated by a distance 1 megaparsec, then they are going away from each other with a velocity 70 kilometers per second at present. So that is the value of the Hubble parameter at present. Okay. Now, sometimes people also sort of, because we exactly don't know what is the value of 70, in this one, we actually find out from observation. So another sort of way people usually write Hubble parameter, the Hubble parameter at present is basically 100 h. Now you see that the h is a dimensionless number, okay? Kilometer per second per megaparsec, okay? And this h kind of means according to the current observer, this h varies between 0.65 to around 0.75. Okay, that is kind of a current limit on h, right? So the Hubble parameter sort of roughly from 65 kilometers per second per megaparsec till 75 kilometers per second per megaparsec. So like instead of giving this h, capital H naught and all those things, people usually sometimes just refer to the small h, which can take value between 0.6 and 0.7. Like if you go to the Planck data, you see that there are quoted values like omega n into small h square, and that small h basically is small h. Okay, so that is one convention that people use, okay, to write down Hubble. Okay, fine. So what else we can do? Because ultimately we obviously we need to solve the Einstein's equation and get the main point is that we're going to calculate this capital this small a, and it gives the how the universe is evolving. Fine. But before that, before going to solve the Hubble parameter, fine. Before we solve the a to the Einstein's equation, what else we can do? Okay. So one very interesting thing that happens due to the the expansion of the universe. So let's say that there are two observers. Okay, let's say there are two observers. Okay, and they are separated by a distance delta L. Okay, and remember whenever I am writing my dl square is basically my dl square is basically s square t into that metric. Fine, whatever the metric that I have. Okay, dr square 1 by kr square. I'm just not writing, but that is my dl square. Fine. So let's say they are separated by a distance L, fine, delta L, fine, and a photon goes from this point to that point. Okay, the photon goes from this point to that point, fine. And as the photon start going from here, it has a frequency omega, fine. But as I know that as it going to this side, fine, there is a velocity in between, okay, because the universe is expanding. The velocity we already calculate. This is this v, fine. This between these two galaxies or two observers are moving away from each other. So this photon, we know that simple redshift, fine, Doppler effect that we have. So this photon frequency will be Doppler shifted, fine. And what will be the Doppler shift? So d mu by nu, so that the Doppler shift will be likely this v by c, fine. And we are putting c equal to 1. So this is just a minus v because all our calculation we are putting c equal to 1, fine. So this is minus. And what is this V? We already know this V. This V is A dot by A into this DL. These are physical. So that is this DL that I have between these two. So this is basically minus A dot by A, okay, into delta L, because H is A dot by A, fine. And what is the DL? The DL is what is the distance that photon travel from here to here. If the time that takes here to here is delta T, so the distance it travels is c into delta t. C is the velocity of the photon and the time it takes, let's say delta t. So the distance dl is c into delta t. I am putting c equal to 1. So in my unit, this is equal to minus a dot by a into delta t. Right? So what I have from here that this is minus delta a by a, because this is basically dA is basically a dot is dAdt, fine. So this is delta a by a. So what I find from here that this photon, as it moves from one point to another, okay, its frequency or wavelength that get Doppler shifted, and that Doppler shifting is basically how it goes. That is, this is proportional to 1 by a. Okay, so they always the frequency actually decrease, so the wavelength increases, and as because higher wavelength, we know that it goes towards the red. Okay, so we is called the red shifting of all the information of the light, fine. So we have a red shifting that is happening. There is a physical effect. What is called, this is simple that the Doppler shifting that we have due to the expansion of the universe. All these galaxies, they are moving away from each other, fine. And this red shifting is basically proportional, the frequency, that change in frequency is proportional to 1 by a. Right? So that is standard thing that we have, fine. And in general, what we have that we can actually, so if I have some photon which is when it's emitted, let's say it is mu, okay, and when it's received, it is, let's say, mu naught. Then we know that that if it's emitted, it is mu, and is received, which is mu, fine. And this should goes as basically, so this is 1 by A, and I said that, let's say that present this is a naught, and at some point it is A, fine. So this as should go, and I put my A naught equal to 1. So this actually goes like fine. Okay. So like A naught by A. This is mu naught A. So this is so this is A by A. Okay. So what you have over here, so what one can do, this redshifting, one can define by 1 plus Z, and this 1 plus Z is basically, you can write this as 1 by A. Okay, A naught is 1. So usually one write it as A naught by A, but this is A naught I put equal to A. So I can write 1 by A. So this is the redshifting formula, how the wavelength gets fetched, fine. This is 1 by A. Okay, and what you can find is that very, very early time when the size of the universe is roughly 0. Okay, so if I take, so very early time, this Z goes to infinity. Today, when my A naught is 1, so A is 1, so Z is 0, and in far future, when A goes to infinity, this Z goes to minus 1. So that is the thing. So what that you can see that with this Z, actually I can get a size of the universe. And as the universe is expanding, okay, so what if I know the present size, let's say it is 1, instead of, in terms of that, I can know whether the universe is half of the size of the today, 1/3 of the size of the today, 1/4 of the size of the today. That gives you sort of a time stamp of the cycle on the universe, and that can be actually related to the redshifting parameter. Okay? So the redshifting or Z can actually related to different time stamp on the universe. Okay, so that's why it's an important quantity. Okay, that's it. Let's see that before going thing. There is any question that is there. Is there any question? Okay, no, fine. Okay, so how much time I have? I have 15 minutes, fine. Okay, so let's now try to write down the Einstein's equation. So my geometry is given by this. S square E into dr square 1 minus kr square plus r square d omega square. And as I know, so I have to write down the equation G mu mu, and I have to write this equal to 8 pi G constant T. This I have to solve. But the first thing that you can see that the universe is homogeneous, okay, and isotropic. So all the 3 directions are the same. So that's why this G mu mu should have a G00, and its G11, G22, G33 has to be the same. Okay. So we should have G00, and this G11 and should be equal to G22, should be equal to G33, right? because of the homogeneity, right? So that should, and as because this Einstein's equation also keeps that symmetry, that means that my T nu mu should also have that feature, right? This T nu mu should also have that feature, okay? That it should have T11, T22, and T33 should be same, and there should be T naught naught, which would be something different, right? So from that, we can actually get a sort of a structure of T nu mu, and that structure I can write as that it has some T00 component, and the rest of the component are basically the same. And they are only time dependent. There is no space dependence due to the homogeneity of the universe. Now this structure that I have written over here, it's a structure for an ideal fluid where one can write that we can actually relate this alpha T as the energy density of the fluid, and these are related to the pressure of the fluid. So keeping in sort of consistency with, I just write like minus, but remember that I am not saying that this P is always positive. This P, if I put it with a ideal fluid and the fluid that we know, then the fluid, the P can be positive, but there can be also situation that P can be negative. So, so it doesn't matter that whether I put minus or minus, this here minus or plus. So P can be positive or negative, just to make things consistent with our signature convention, where I have taken plus, minus, minus, minus. I just put here minus. So this is the structure of the T nu mu. Fine. That just comes from the homogeneity and isotropy. Homogeneity says that there is no x dependence. Isotropy says that the three space components are same, are equal, right? And with that, I can write down the Einstein's equation. So that you can do. You can take this metric, calculate the whatever the G nu mu, and the T nu mu is this, and you get basically two equations. Okay, as I said, there is one equation coming from G00, the other equations, any of the equations that we have G11, G2, G3. Okay, and with some sort of a algebraic thing, you can get two equations, two Einstein's equation. Okay, one is, I'm just writing, so one is a dot square by a square plus k that I have, a square is equal to 8 pi g by 3 rho t. That is one equation, and the other equation is minus 4 pi g by 3 plus 3. So these are the two equations that you can get from Einstein's equation. Right? Now just a little bit look at these two equations. First of all, as you can see, so this equation is basically gives you the first derivative. It's a kind of a constant equation that you can have. The second equation actually gives you the dynamics. It gives you the second derivative or the acceleration term. Okay, and as you can see in the acceleration term, there is no curvature dependence. Right? So whether the universe expansion is decelerating or accelerating, that not at all depend upon what is the space curvature that you have. Whether universe is a flat model, whether it's a closed model, or whether it's an open model, the A double dot doesn't take care of that. Okay? A double dot is independent of the curvature, so it doesn't depend upon the space curvature of the first thing. The second thing is that you can see that we have two equations that I have, but the number of unknowns that I have is A, rho, and T. Okay, so there are three unknowns and there are two equations. So obviously one needs another information to solve this equation. And that information can be given. That information is basically comes from the fact that how this P and rho are related. Okay, and that is sometimes called the equation of state of this fluid, which is basically how P is related to how the pressure is related to the energy density. We will discuss three very common scenarios that we believe that is there in the universe. But once this equation of state of this fluid is given, then your system is closed. Fine. There are two equations, and then another constant in another equation coming from equation of state. So you have three equations and three unknown. I can solve it. Fine. Things start getting complicated. So this is just if you have only one fluid, fine. But things start getting complicated when you can have more fluids in the universe. Maybe you can have matter in the universe, you can have radiation in the universe, you can have dark energy in the universe. So the equation number is the same, but then there starts coming into play that there you have a rho for matter, a P for matter. So there's these two unknowns. Then a rho for radiation, there is a P for radiation, then again two unknowns. And then there is a rho for dark energy and there is a P for dark energy. Again, there are two unknowns. So there are around, so there are more number of unknowns, right? So in that sense, if I assume that all these quantities are not interacting with each other, then I can define all sort of equation of state in between there, and then I can solve this system. Okay, but things may be more complicated when they are interaction into, let's say, matter to dark energy or whatever. Right? And then you cannot define an equation of state individually for a matter for dark energy, and things system get a bit complicated. But But for the time being, we just assume that all these quantities are not interacting to each other. They have their typical domain when they are dominating, and then we can very easily solve this system, right? So that will okay. There is another important thing that you can actually straightforwardly see from here, that if this rho and 3p or p, okay, we believe that for normal, whatever the matter that we can have, all these galaxies or stars or whatever we have in the universe, all lot of radiation that we have, the CMB photons, or if there is some massless neutron, whatever this normal matter you can have that we call matter or baryons or radiation. For all those things, this rho and p, they are always positive. So both rho is positive and p is positive. Okay. So if these both two things are positive, then this A double dot is always a negative term. So that means the expansion of the universe that we are having is always a decelerated expansion. So the velocity is actually getting smaller and smaller. Right? So what we have A dot positive, okay, for a normal matter, radiation, whatever here, A dot positive, so the universe is expanding. At the same time, A double dot negative, that means this expansion is actually slowing down. Okay. Now, what these two information can give, what we can do, right? So let's say that I draw, this is T, and let's say this is AT. Okay. And let's say at some time, let's say this is my present day at T dot. I give you the A dot. Okay, I give you the A dot. Okay, so the slope here, so the derivative of this thing. So I give you the A dot at T dot. Okay, I give you that. So that is the slope that I have, fine. Now I ask you that I give you at this point this A dot, the slope, which is a positive value, right? Universe is expanding. What I can get to know if I go in the past, given this Einstein's equation, Okay, so at present I give you what is the expansion rate of the universe, A dot. I know this is a positive number, right? Okay. Then what I can get to know about the past in the universe, right? What happened, let's say, when the universe is some 16 billion or 20 billion years ago or act, right, from today, right? What we get. Now, as you can see that if I have this A dot that is given over here, some slope, and I said that if the universe is remain in that slope, so it will just go and sometimes it will hit over here, fine. So it means that if the universe remains at that A dot value throughout the history of the universe, so you have the same. Otherwise, either this A dot will increase in the past, so you can have some sort of a value where this A dot is actually increasing, or this A dot can decrease in time, in the early time, so that A dot can go this way. Okay. Now, what it actually does for normal matter and radiation, we already know that A dot is a negative number, right? Because A double dot is negative, so the A dot is a negative, right? So this rho plus 3p, if my rho and 3p is positive, then this A double dot is negative, right? So that means what we actually know, if universe have normal matter and radiation and everything, then at some point in the past, the universe will actually, this will hit over here, right? It bound to happen, right? It should hit a little, because if this A dot remains the same, then it will hit at some point over here, okay? But we know that the A double dot is negative, so it will always hit at something earlier than this point, right? Okay, so that will always happen when the A will be actually zero. Okay. Now, what is this value? What is this value? Fine. This value, as you can see, this is my current present time. So this value is the present day scale factor. This I know the slope, okay, which is the A dot, and this actually gives you over here, fine. So these actually you can do readily, very small calculation. You can show that this value is a 1 by H dot. Okay, so this time is, because H dot has a dimension 1 by time, so this value is related to 1 by H dot. It's basically 1 by H dot. So what I can say is that if the universe having all this normal matter and radiation, right, then the AT will hit 0. The AT will hit 0 in past, okay, within an age Because the maximum time that this means it will be within that time or most probably less than that time, within an age which is maximally bound or bounded by 1 by h naught. Okay, so maximum 1 by h naught that is just means it can go fine. Means when a dot, I mean a will be 0, but it will at least less than 1 by h naught means it will always hit. The a will always hit. It always will happen. Okay. Just from this equation, we can actually conclude. So what we can actually conclude is that if there is something extra or something other than that, when rho plus 3p will be negative, it happens. If rho plus 3p is always positive, right, in the past, right, when we have normal matter and radiation, then the scale factor of the universe should always hit to 0 at some point in the past. Okay, and that value can always be smaller than 1 by h naught. Okay, so whatever the age, so if I know h naught, so I can calculate what is the age of the universe from 1 by h naught. So that value will be always roughly smaller. So what we know now at the present, that the age of the universe is basically around 14, 13.8, 14 billion. So by that time, universe should always hit, the age is always hit to 0. Okay, so if I tell you that, okay, I give you a dot today, and let's say what is the behavior of the universe when universe is 20 billion years old, you cannot tell me, because before that time, the universe, the scale factor will go to 0. And if the scale factor go to 0, all the physical quantities, you can show actually that the curvature actually blows up. Right? So it can go to an infinite curvature. Okay, one can show that all the physical quantities like density and others, they actually hit to infinity. So there is a singularity always at the past. At a finite time. Right? So there is a finite time in the past when we hit a singularity, and that singularity is a physical singularity. We'll find all the space-time curvature will actually close up. Right? So that is a problem in this Einstein. We also have this singularity in the black hole case. When r equal to 0 is a physical singularity. Right? Here also is a singularity, physical singularity is there at that point when the a goes to 0. Okay, there's a singularity. So now what is the problem? So the thing is that whenever we have a differential equation, this is a differential equation, second order differential equation, we need to solve it. We need to initial condition. But as you can see that we cannot put the initial condition in the past on that, because there is always a singularity that is sitting over there. Okay, and at that singularity point, things get blown up. Right? So we cannot put an initial condition at the past. Right? So if you want to do that, if there is something that we need to sort of save from this thing, means there should be some process in the universe when the a dot actually start increasing or the a double dot is positive. Right? And once you do that, once you allow, then many things can happen. Right? And that picture is what is called the inflation that we will learn from the next other lecture. Right? Where we can have an inflationary period in the universe where we can actually avoid this thing. Right? But other than that, if there is no inflationary period of there, it is actually that the universe will always hit this singularity. Okay? And that Big Bang singularity is always there. And due to that, it's difficult that we can solve this equation putting the initial condition. We can solve this equation putting the initial condition in the past because there is a singularity sitting over there. So we cannot do that. Okay. So I stop over here. And you can ask questions. Okay, so I stop now. It's more or less 1. So I stop over here. The rest of the things that we can go from here, which is basically to solve Einstein's equation and define quantities that we can define. That we do at 30. But you can ask what if you have other questions also, or you can write at the chat box.
Can we mute ourselves? Or say
You can you can unmute and you can ask the question.
Sir, my first question is, what is the physical advantage of the scaling of the K in small scale?
Yeah,
What it has you have
it's not
discussed
small
that.
scale. It's not small scale. Means I just make this scale the K so what I did. It will go.
So it was just for make it dimensionless or in a
Yeah, because
physical
see
terms?
that I have here, so I have here a term which is dr square 1 minus capital K r square, fine. And I said this capital K is related to these three curvature, fine. So this is the constant, and this capital K is related to this three curvature, fine. So it has a value, fine. Okay, and it's a dimensionful quantity, fine. So I can carry on all these calculations. There's no problem with that. But then at each point, I have to be careful that I have to take account of this dimensionful quantity with a value sitting over there, right? So if you can do it consistently, there is no issue. You get same result whatever we are doing, right? There is no issue with that, right? But sometimes like this K appears in some sine function, this function and that function, right? So if I instead of that, if I have a dimensionless number, then it is much more easier. Otherwise, I have to always take care of that there is a dimension sitting quantity sitting
It
over
will be
there.
easy to choose 0, -1, +1.
Yeah, so that I did. So now if I have this, if I have defined this small k, which is this k divided by its magnitude, fine. Then I know that if k is 0, this is 0. If for other value, it will be either +1 or -1, right? Depending upon whether it's a positively curved or a negatively curved. Right? So then it has a value 0, 1, and -1. I don't need to be that careful. So I know that these values should be always like that. Okay. So in my calculation and all those things will be much more important. Otherwise, you say that, oh, I don't want to do that. I will keep capital K as it is, and I do all the calculations. You will get all the results as it is coming up. But then you need to be at all point, you need to be careful that there is a capital K with a dimensionful quantity, the value is sitting over there. Okay. So you have to take care in that every
Thank you,
calculation.
sir. Thank you. And another question is that in the Z00 term, because
What?
you have said
Again?
so G00, small z00 in metric
Okay.
terms.
Yes.
So in a special relativity, we have taught that it is just observing the same frame of the incidents. So is it test frame and moving frame is same here. That's why we are.
What we have, so if you have this ds square, fine. So
Yes.
I know this ds square is basically c square d tau square, fine. But this tau is a proper time, fine. From the special relativity, and for my case, we are putting c equal to 1, so ds basically is the proper time, fine. Okay. So now I write down the metric, then I need to set an observer, fine. So I take those observer, so that I take those observer, that observer are x alpha equal to constant. So their observer are actually sitting at rest, fine. And I use their clock as the proper time. Okay, I use their time as the proper time, and then that makes me that G00 is 1, fine. You can also say that I have this G00 dt square, fine. Mathematically, it is nothing but that because of the homogeneity, this G00 can be only function of time, fine. Because there should not be any space dependence, fine. So G00 can only be function of time. So I can define this, and then I can redefine my time in a sense that I can redefine my 00 dt as my d tau, right? And this is now, I said that now from now on, this is my time. Because I can always redefine my time coordinate, right? And if I do that, then one can show that this is actually the proper time of all those observers which are sitting x alpha equal to constant.
Yes.
So that is the thing. Only thing
there is observer in the same co-moving.
Yeah, that is co-moving observer. So these observer actually moving with the expansion. So for them, so they are static. They are at rest, right? But just I have not mentioned, but there's the important thing over here is that. So I said that I have this co-moving observer, fine, and in this observer, my x alphas are constant, my t is basically my proper time, and I see my inverse is expanding. And inverse is homogeneous and isotropic. So using that observer, that time frame, then I write a metric which is basically homogeneous and isotropic, right? Then you can ask that, okay, now if I have another observer which is moving with a velocity with respect, uniform velocity with respect to this observer, whether he or she also sees that the inverse is homogeneous and isotropic. Actually, it is not. Okay. Okay, so here in that observer will not see that the universe is homogeneous and isotropic. Okay, so in a sense, what I am doing is basically that I am choosing a particular Lorentz frame. Okay, and in that sense, you can say that, oh, you are violating. So we have a preferred Lorentz frame, so Lorentz invariance is violated. Fine, that because I am choosing a part, because all those other observer basically will actually will not measure the homogeneous anisotropy, right? So I have a particular observer that I am choosing that have a homogeneous anisotropy. Okay, and I am doing every calculation with respect to that observer. Okay, in fact, you can, when you do the CMB, you can actually, you will see that actually this happens, because you can have an observer. Let's say CMB, I measure the CMB temperature, and then if I am moving to some direction, then there is a photon that is coming from behind me and the photon that is coming from in front of me, there will be difference. And I can calculate this, what is called this Doppler isotropy. You can actually calculate. So you can actually calculate your velocity measure with respect to for the CMB frame. Okay. So in special relativity, we know that there is no absolute frame. Fine, we cannot calculate anything. But actually here we have a CMB frame over which you can actually calculate the velocity. But thing is that this is not a problem. Fine, because ultimately I am solving G mu. My general relativity is actually have this general covariance or general coordinate independence. Everything is actually satisfied. Only thing what I am doing is that I am taking a particular solution where so in a sense, and that's why I have a particular knowledge frame, and I am doing this calculation in that way. Right? So you can do that. I can do some another frame. I do all the calculation. But you will see that all the physical measurable quantities are all the same. They don't change. Okay. But in this case, we are actually, by doing so, we are actually choosing a preferred observer or preferred Lorentz frame where this homogeneity and isotropy is having. Okay. But in principle, you can choose other observer also. But then you do all the calculation consistently, you will see that your physical result doesn't change. Because ultimately, we are solving Einstein's equation, which is a general coordinate independence is there. So that is always there. Okay. But for a particular solution, we are a preferred knowledge. Any more question? Okay, so another question is that can we avoid the physical singularity using mutation? Actually, one can see, because what we have over here, that as you can see from here, right? When let's say here. So just come over here. So what we actually assume that we see that this thing has this sort of a curve, right? Because of the fact that the A double dot is positive, A double dot is negative, right? Rho and P is positive, so rho plus 3P is positive, A double dot is negative, and that's why from here as you go past, it actually hit over here, right? But now let's say that somehow I have something happening in the universe at some point in the time, in the early time or whatever, when this rho plus 3P is not positive, right? Rho plus 3P is negative, let's say, okay? If the rho plus 3P is negative, then this A double dot is positive. And if the A double dot is positive, obviously then it will not go like that, but it will actually start increasing. Right? If I have A dot over here, it will actually start increasing. So what actually happens in the universe, in the inflationary case, there is a matter radiation equality up to some time when the universe is actually this A double dot is negative, so it actually falling like that. But then if I go to a very, very early time, then this rho plus 3P becomes negative, so A double dot becomes positive, so it starts increasing. Okay? So it actually falls down due to matter or radiation, but then it starts actually increasing. And if it start increasing, then obviously before it hit over here, if it start increasing, fine, then obviously you can actually avoid this singularity. So, but then there are other problems in setting up the initial condition that you see. But taking into account that if I can have somehow the rho plus 3P negative and this become positive, then I can actually heat. I can avoid this heating actually. Okay, it can, because from today, maybe it is going down. till when rho plus dp is positive, but when rho plus dp starts coming negative, becomes negative, it starts increasing. So it may not hit, it will not hit that A equal to 0. Okay? It can have a minimum, but it will not hit to 0. Then it's starting. Any other question? So please go through these things. This Manavendra has told you that for your there's a Python notebook and some text file giving you, so that we'll use for today's tutorial. So in 2:30 we'll start first doing a little bit about the cosmology, the rest of the thing, and then we do some sort of a hands-on and just go through that. Okay. Any other question you have? Anybody?
Sir, I have another question.
Sure.
So, why we cannot take the capital G mu average instead of the small G mu
No.
average function of?
No, as I said, so you can take it. People have, because when the dark energy and late time acceleration starts, means all these data comes and people say that there is a late time acceleration and maybe due to that dark energy. There are many works where people say that actually this is not a dark energy, but maybe this is actually the issue, is that this is the averaging that we are doing, which are not doing the property. Right? So they are working, not that. As I said, we still don't know why it actually works, but the fact is that the way that we approach, so that we take the Gini averaging first and then do all those average thing and do calculation. These are all, I mean, like consistent work, and from there, whatever result we get, and they are very much consistent with the observation. You can do that part, right? People have tried that thing, people have done those things to explain dark energy and all those things. And then to explain dark energy, you need to average it over some kind of a scale, so that you can explain whatever the dark energy effect that we see in the universe. Okay, that may not be averaged over some 20 megaparsec scale, but some other megaparsec scale. Fine. So those effects people have tried to do. Okay, so there are a lot of work, but the fact is that this actually makes things much more simpler. The approach is much more simpler. So we can actually make further, we assume that, okay, we take the average of Gini fast over a box size, say that 10 universe is homogeneous and isotropic. Then I solve the Einstein equation, and then I build in homogeneity over there perturbative. So I say that, okay, this is my background, then, but I know that there are structures in the universe. So I start perturbing this metric, and I put this perturbation, first order perturbation, second order perturbation, or whatever. I start doing. And this, by doing this way, it is, I mean, like till now, whatever the observation we have and everything, it is perfectly consistent. Okay. And that's because this thing works, so people usually do it this way, right? But as I said, still we don't know why it actually gives this perfect result. But there are also approaches where people did the other thing. So people first try to write down all the inhomogeneous equation and then average it over, and then write a averaged Einstein equation, and then you see that due to those averages, there is some new terms are coming, and then people try to explain those new terms as a dark energy, and then people say that, okay, there is no dark energy as such, but due to this process, there will be some new terms coming in Einstein equation, which are not taking into account. And that may explain all those effects that we see in the supernova. So that approach is also there. Okay. But the approach that we are following is, till now, it's actually completely consistent with whatever we observe. We can make models, we can predict things.
Sorry, sir. Whatever you have said, that the extra part for taking average of capital G mu, that is the effect of the effect on geometry between for dark energy field.
Yeah, there is some noise coming. Yeah, so yeah.
Oh, I got it.
Yeah. Okay.
Thank you, sir. Thank you very much.
Any other question? Okay, so if not, so we'll meet at 2:30 again. Fine. Okay. So okay, we'll see that you go to this tutorial Bhaswati, so you will see that how it works, right? So in that thing, you don't need to have a Python, because that is there in the Google Colab. So the Google Colab and the Python. So Manavendra will help you see what it happens.
Okay, thank you, sir.
Okay, see you at 2:30.